Welcome to this lecture where we are going to discuss about the tubular heat exchanger and the various types of tubular heat exchangers those are present in the market. So far we have talked about different heat exchangers, design methodology and analysis, and we have seen that most of the time we are taking the heat transfer coefficient or the friction factor that is already given. But in reality we will find that those are the parameters which are to be determined, and first of all we will start with the geometry which are very simple and gradually we will go into the complicated one. So, we will start with the tubular heat exchanger, where the simplest geometry that we have already discussed about is tube in tube, or more commonly known as double pipe heat exchangers. Then we will talk about the shell and tube heat exchangers, and another variety of it is the spiral tube heat exchangers. So, before going into the details, we will just try to have a look into these exchangers, how it look like in reality. So, the double pipe heat exchanger, if you look at, this is a heat exchanger, it is a double pipe heat exchanger, where you can see you can understand the size of the exchanger from this diagram, that, and you will find that the tubes are coming, or the fluid is coming from one end to the other end through this bunch of tubes. If we just try to look into it schematically, we will find that one fluid will be entering from this end, and that fluid will be flowing through this inner tube from this end to this end, and it will come out from this side. That is about the other fluid. This is, say, one of the fluid streams. The other fluid stream will come from this end. So, it will enter here into this heat exchanger, then it will flow through this annular space. If I take a cross sectional view of this one, we will find that there is an outer tube, this is the inner tube, and this is the annular space through which this blue color fluid is flowing, and it will come like this, and finally it will move out through this end. Now, depending on the direction of the flow, it may enter from this side and it may come out from this side, or it may enter from this end and finally come out from this end. So, during the initial phase, you can understand that if the fluid is entering from this end, this will be in parallel flow in combination with respect to the second fluid. Whereas, if it is entering from this side, you will find this will constitute a counter current configuration. Whereas, if it is entering from this end, this will be in parallel to this flow, and that will make a parallel flow arrangement of the heat exchanger. So, this is the simplest possible geometry, where we call it double pipe heat exchanger, or often it is called double pipe hairpin heat exchanger. We know the hairpin, like it looks like a pin like this, and this is similar to that configuration. So, that is why we call it hairpin heat exchanger. So, this is one of the simplest geometry that is possible with the this heat exchanger. And then if we look at, I mean, this is another configuration, this is from the bound fin tube company, and this is another double pipe hairpin heat exchanger, in reality how it looks like. And depending on the configuration, what I mean is that, say, this is some of the characteristics of this heat exchanger is that this type of exchangers are in use when we need a small heat transfer surface area. Also, the this particular type of heat exchanger is suitable for high pressure fluid streams, when both or one of the fluid stream is bearing very high pressure, and we can think of using this kind of exchanger. On the negative side, what we have is it is bit bulky and it's bit expensive per unit surface area. Typically, it is having about say 50 meter square of surface area, and about this when we need typically of this kind of surface area and high pressure fluid stream, we go for such kind of heat exchangers. And it's, as I have said, that it is bulky and it is a bit expensive, otherwise it is very simple, and these two are the supports which will keep it in horizontal position or in position. So, one fluid will be entering from this end and the other fluid will be entering from this end, or it may also enter from this end depending on the counter current or the parallel flow arrangement that is to be made. Now, here in this if we take a cross section from this end, you will find that it may so happen that this annular flow, annular passage may have a single tube or it may have a bunch of tubes like this. This is also possible. We may have, depending on the configuration, we may have bunch of tubes or a single tube. So, it is not then double pipe, it will have multiple tubes, multiple pipe. And it may also have, depending on the heat transfer coefficient of this annular space, if we find that the heat transfer coefficient of this annular space is small, then we may have to use extended heat transfer surface or fins on this side, on the outside of the inner tube. This is particularly for a single tube or multiple tubes. So, this extended heat transfer surface will try to compensate that smaller heat transfer coefficient on the annular space. So, depending on the process requirement, we may go for an extended heat transfer surface or finite tube configuration. We may also go for multiple tube configuration of this double pipe heat exchanger. So, next is the shell and tube type heat exchanger. It is one of the most common configuration we commonly look in get in the industries. So, here you can see that we have a shell and we have the tube. We have bunch of tubes, this is the tube inlet through which the fluid will enter to the heat exchanger. This is the tube side, and we have, this is the tube sheet. In the tube sheet, we have the holes through which all these tubes will pass through. There is also another tube sheet on this side. So, this tube sheet will have holes through which this tube will pass through, and in between, this whole tube sheet on both sides will be enclosed by the shell. Now, the shell side fluid will enter from this end and it will come out from this end, or it may also have a different configuration, or it may it is also allowed that the fluid may enter from this side and it may come out from this side also, depending on the configuration. Now, this is the tube side fluid going in and coming out, and locally the shell side fluid, this is a two fluid configuration where the shell side fluid is coming and passing over the tubes. These are the baffles, these are called the baffles. So, as we have written here, these baffles will try to arrange the fluid or divert the fluid from one end to the other like this. It will be flowing like this from one end to the other end. So, if we look into, if these baffles are say not there, if we imagine that we have removed this baffle. So, what will happen? This cell side fluid will come in and it will flow like this in parallel, or it is in the counter current configuration if it is entering from this end, and this will be flowing onto this side through this annular space and it will come out. So, it will be basically a counter current or parallel current arrangement, but if we look at the staying time of this fluid, it is very small, whereas on this side if we have baffles, it is coming like this, it is a cross flow, and then here this is a counter current arrangement, then again it is flowing in cross flow, again it is in counter current arrangement, then cross flow. So, this cross and counter current arrangement will allow the fluid to stay for longer time and have a larger heat transfer time. So, as a result, what will happen? We will find that obviously the heat transfer will enhance, but at the same time we will find that the pressure drop penalty has also to be paid. So, this is what is in a nutshell about the shell and tube heat exchanger. There are different kind of shell and tube configurations which we will be dealing later on. That, as you can understand, that if this these are the tube sides and this is the cell side, these tube sheets and the shell, if they are welded together and if there is differential temperature, I mean between, obviously there will be differential temperature between the hot and the cold fluid, but if that difference is very large between the shell and the tube, that may result in some kind of expansion, which is or say the thermal stress may be generated, and which if it is not designed properly, that may be disastrous. So, we may have to design it in such a way that the thermal contraction or thermal expansion due to differential temperature between the shell and the fluid type, I mean full fluid flow, can be taken care, and it is not generating generating some kind of thermal stresses which is not good for the heat exchanger. So, now we will try to move to the third one. This is spiral wound heat exchanger. You can look into the size of this particular exchanger. It is just not larger than just a fingertip or a small finger, and this kind of exchangers are in use particularly in cryogenic. Both these examples have been taken from the cryogenics. This is typically a Jock-Hampson heat exchanger. This is a spiral tube exchanger, whereas this is this particular Jock-Hampson tube heat exchanger. I mean, it is a tube exchanger or tubular exchanger without any fin, whereas this particular spirally wound heat exchanger, it is having integral finite tube. So, this is spirally wounded on a mandrel as well as that is having integral fin on top of it. we call typically this is called JT cooler heat exchanger. This is a JT cooler and this is called Jock-Hampson heat exchanger. So, we will not go into details of this one at this moment. We will rather look into the as we have said that we will try to find out what is the heat transfer coefficient available for both the shell side or the tube side. So, first of all, if we look into this all this tubular heat exchanger configuration, we will find that one of the fluids is passing through the tube, whereas the other fluid is passing through the shell side. So, what we need to look into is the internal flow, and sometime we also need to look into the external flow. So, one fluid is flowing inside this tube. So, when we talk about the internal heat transfer coefficient, and also this is the valve. Most of the time we neglect the resistance offered by the metal of this valve, and we also have the external heat transfer coefficient. So far in our analysis, we have assumed that this heat transfer coefficient has already been given to us, but this time we are trying to find out how these heat transfer coefficients are known or how these are to be estimated. So, here for the internal flow we have some kind of correlation. For the external flow, depending on the type of fluid flow, we will have a different type of heat transfer coefficient, and for the internal flow we have different type of heat transfer coefficient correlations. So, first of all, we will try to look into the internal heat transfer coefficient, and there are different type of correlations available in the different textbooks. You will be able to follow you can follow any one of them. Now, when we talk about the internal flow through a circular tube, what we need to know also how is the flow condition, whether this flow is laminar or the flow is turbulent. Depending on that, the heat transfer coefficient will change. So, what is the transition? How will we know whether it is in the laminar flow or in the turbulent flow? So, first of all, what we need to find out is the Reynolds number. It is a dimensionless number. We often call it RE, the Reynolds number, and we define it by GD by mu, where this DH is the hydraulic diameter, it is called the hydraulic diameter, and we define it as 4 times the free flow area divided by weighted perimeter. So, this is how we define the hydraulic diameter. What is G? G is known as the mass velocity. This is mass flow rate per unit free flow area. So, this is how we define the mass velocity and mu is the viscosity of the fluid. So, if this Reynolds number is less than 2300, 2300, then for a circular smooth circular pipe, we assume that the flow is a laminar. So, if it is having a laminar flow through this circular pipe or circular tube, we will assume that it is laminar and the friction factor will be given by 64 by Re, where Re is the Reynolds number. And why do we need this friction factor? Because in any heat exchanger design, one of our concern is the pressure drop, and we define this pressure drop as F L g square by 2 rho and then the hydraulic diameter that we have defined. So, this F in case of laminar flow configuration through a circular pipe, we will be using 64 by Re. We have the g as the mass velocity, L is the length of the tube, and this rho is the density of the fluid. So, this is how we calculate the pressure drop across the length of the tube. So, now let us look into the Nusselt number. This is again a dimensionless heat transfer coefficient. This is a dimensionless heat transfer coefficient, and we define it by h d by k, where h is the heat transfer coefficient, d is the hydraulic diameter, and k is the thermal conductivity of the fluid. So, this is given by 3.657 plus 0.0668 Grudge number divided by 1 plus 0.04 ZZ to the power 2/3, where this ZZ is called Grudge number, and we define it as Re into PR and d by L. I am sorry, this is d by L. This is what is the Grudge number. So, this is about the laminar flow region, and when we have the turbulent flow, in that case this friction factor will be 0.316 Re to the power minus 0.25, and this is for the Reynolds number range between 3500 Re less than 2 into 10 to the power 4, and for Re greater than 2 into 10 to the power 4, we have this F equals to 0.184 into Re to the power minus 0.2. So, these are the correlation for the turbulent flow, where we understand that the friction factor values are like this. So, if the Re range is between 3500 and 2 into 10 to the power 4, we have this kind of the friction factor, and similarly we have when the Re is on the higher side more than 2 into 10 to the power 4, we have 0.184 Re to the power minus 0.2. And what is about the friction fact. What is about the heat transfer coefficient? The heat transfer coefficient, we can generally it is either defined in terms of the Nusselt number, or it is often defined in terms of the Cold-Burn J factor. It is given by H by G C P, where H is the heat transfer coefficient, G is the mass velocity, C P is the Stanton number. This is nothing but Stanton number into Prandtl number to the power 2/3. Cold-Burn J factor. So this is what we will find as 0.023 into R e to the power minus 0.20. So, this will become, if we express it, this J is also this J can also be written as the Nusselt number divided by R e to the power 1/3. Okay. So, this becomes, if we want to express it in terms of the Nusselt number, then the Nusselt number becomes 0.023 R e, it becomes R e to the power 0.8 and P r 1/3. So, this is in terms of the Nusselt number, or in terms of the Cold-Burn J factor, this is just J h equals to, as we have said, 0.023 into R e to the power minus 0.2. Okay. Now, all this J h, or say the Nusselt number, as we have written for the turbulent flow, all the fluid properties are evaluated at the film average temperature. What is film average temperature? It is the average fluid temperature this is T f is average fluid temperature plus T wall temperature divided by 2. So, this is how we evaluate this film average temperature, and all the fluid properties have been evaluated at this film average temperature while calculating the Cold-Burn J factor or the Nusselt number. So, this is very important so far as the estimation of these fluid properties are concerned, and we should not deviate from that film average temperature for evaluating the fluid properties. Otherwise, we may have a possibility that we will be calculating a wrong Cold-Burn J factor or the Nusselt number. So, this we have to keep it in mind. Now, if we go back to our discussion, here we will find that this is when we talked about the internal flow, whether it is laminar or turbulent, we have the internal heat transfer coefficient in terms of the Nusselt number or the J factor, and from there we would be able to calculate the heat transfer coefficient H, that will give you the internal heat transfer coefficient. Now, if we have a bunch of tubes and over which the fluid is flowing on top of it, then we may have to, I mean, if we have to calculate the heat transfer coefficient on the external flow, then how do we do that? So, depending on the configuration, we may find that these are the two possibilities, I mean, in which in one of the flow configuration we will find that this fluid is flowing on a bank of tube. This is the cross sectional view, and these are the I mean, fluid flow direction. This is the internal flow through which fluid is flowing, and this is the external flow. This is how it is flowing through this over the tubes, over the tube banks. This is called, this distance between the center line distance is called the transverse pitch, and this distance between the two consecutive tubes in the flow direction is called the longitudinal pitch, and D is the external diameter of the tube, and the frontal velocity or the free stream velocity is V, and let this be flowing at a temperature T infinity. So, if it is so, this is the inline flow where the fluid, I mean, the tubes are arranged in line to the I mean, one is just after the other, or it is all of them are in line. So, this is called the inline configuration. We may also have a configuration like this, where they are just offset, this second row of tube is offset, and it is just in between the two fluids. I mean, the two tubes, there is the third one, or the second row tube is just in between the these two tubes, this tube and this tube, and this is the third one. So, they are forming like a triangle. So, here they were forming a these four were forming a kind of rectangle, and this is forming a kind of triangle. And depending on this angle, I mean, we may have a different flow arrangement, and here I mean, the heat transfer coefficient is possible. So, we have the transverse pitch, we have the longitudinal pitch. For this is the longitudinal pitch, the center line distance between two consecutive tubes in the flow direction. We also have another length, this is the diagonal length called SD, and this is also important in case of this staggered flow configuration or staggered configuration. So, here what we now consider that depending on this inline or the staggered flow configuration, we may have different heat transfer coefficient possible. So, let us first try to find out what is the what is there in the inline flow configuration. So, before going into the heat transfer coefficient, we will find that it is important to know what is the maximum velocity, because that will be used to calculate the Reynolds number. And if you look at this Reynolds number, where if it is either in terms of say, as we have said that we define it, the Reynolds number we have defined it as G d h by mu, and here this d h is the external diameter of this tube. And what is the G? G is the mass velocity. So, here the velocity of the fluid is V, and it is flowing over a bank of tubes, and we need to find out what is the free flow area, or if we look at, we need to find out what is the maximum velocity that it is giving. What is the maximum velocity how will we find? So, whether it is occurring, as you can understand that this maximum velocity in this particular configuration is supposed to occur at this location, where we have the minimum gap. So, the velocity of the fluid is taking place from this direction, and here we have the minimum free flow area. So, that will constitute the maximum velocity at that point. And how do we find out the maximum velocity? We know that the total mass flow remains constant. So, if we write it in terms of this AFR is just nothing but the frontal area multiplied by the velocity, and the density, this is just nothing but the mass flow of the incoming fluid, and if it is the flow rate is remaining constant. So, here this A1, that is the area at this point, and here you have the velocity, say V max, and corresponding the density is rho. So, we have a relation for the V max related to the frontal area and the minimum free flow area. So, minimum area is, if you look at in terms of the pitch, we have ST, that is corresponding to the frontal area, and the minimum area is just nothing but ST minus this length and this length. So, that will constitute D. So, ST minus D is the in the denominator and multiplied by V. So, V max is becoming ST by ST minus D into the frontal velocity or free stream velocity. Similarly, now if we look into the staggered configuration, we have two possibilities. The free flow may occur at this point, or depending on the configuration, there is a possibility that the minimum free flow can also be at this location. So, we have to look for these two possibilities. I mean, one is already that we have seen that if it is A1 and this is the other possibility A2, if we have a free flow area depending on the configuration, if A2 is the area where we are finding the minimum area and the maximum velocity. So, in that case, how the velocity looks like. So, if it is for if we go back to our previous slide, this is if we have the minimum at, say, I am sorry, if we have the minimum free flow area or the maximum velocity occurring at this point, then we have already looked into this configuration that A1, if it is at A1, then we have the V max equals to ST by ST minus D. The other possibility is, as we are talking about, that if we have the free flow area occurring at this point, then this flow is coming here and this flow is coming over here. So, it is getting divided into two parts. So, if we write that same equation, we now have V max is equals to half of frontal area divided by A2, where A2 is this particular area, and this is obviously related to SD, and this SD you will find, you will be able to relate it with the SL and ST. So, we have V max is equals to half of ST by SD minus D into V. So, and when will it happen? What is the condition? Now, if this area A2 or this is A2, this is also A2, and if twice A2 is smaller than A1, then only this is nothing but A1, then only we have this maximum velocity occurring at this location. So, if we just solve this one, we will find that this is constituting a condition that 2 S d less than S t plus d, that will give you a minimum flow area at this A2 or maximum velocity at A2. Thank you.